Good morning, good afternoon, good evening, everyone, wherever you are. My name is Stan Chung, and today I'll be presenting our most recent work in realizing ultra-power efficient heterogeneous 3,5 silicon deinterleavers for DWDM optical links. I'd like to thank all of my colleagues listed here for their contributions. So to start things off, I put together a sort of motivation slide. At HPE, we've announced the commission of several exascale supercomputer systems for various government agencies within the US. Just to name a few, the Aurora system here at Argonne National Labs is expected to exceed 2 exaflops by 2022, and El Capitan at Lawrence Livermore National Labs will exceed 2 exaflops by 2023. So we're continually looking at new optical technologies to integrate electrical to optical interfaces that can deliver higher data transmission with improved power consumption across supercomputers. And so today we'll talk about some of the more long-term outlook of these future enabling optical technologies. So shown here is what a typical ring-based DWDM architecture might look like. And we have two versions, with one being on the top and the other on the bottom. And you have a wide comb laser source, and you can either deinterleave the wavelengths or power split those combs into a spatially separated bank of high-speed micro-ring modulators. So the signal is then sent over through optical fibers and then into a receiver, which consists of various types of photo detectors. Now, on the receiver side, there are issues with the polarization diversity, but those are details we won't get into in this talk. So at Hewlett-Packard Labs, we've proposed a novel DWDM architecture with the goal of full integration capable of 1 terabit per second data rate and less than 1.5 picojoules per bit energy efficiency up to an operating temperature of 50 degrees C. And so some of the differentiating technical concepts are itemized here. Obviously, DWDM plus spatial division multiplexing with a single quantum dot source that can be either off-chip or on-chip, but we prefer on-chip. And one of my colleagues, Geza Crixville, is leading that effort. Also, NRZ of medium bandwidth modulation per wavelength. And then we're also going to include integrated 3.5 slash dielectric slash silicon MOSCAP capacitors, and that really enables athermal and efficient channel control for a lot of the devices on this chip, such as lasers, modulators, and deinterleavers. And this enables efficient NRZ modulation of our 3.5 silicon micro-ring modulators indicated here. We'll also have germanium and 3.5 semiconductor co-integration on silicon, and then also multiple sources and detector flavors. The sources being monolithic, heterogeneous, or a combined version of both. And then for the detector side, we have silicon germanium or quantum dot avalanche photo detectors indicated on the receiver part of the chip here. So there's actually quite a few components that go onto this chip, as you can see. So in this talk, we'll focus on just the wavelength deinterleavers. So here's a slide summarizing the landscape of state-of-the-art DWDM silicon deinterleavers. Now, it does say a complete survey, so I apologize if I've missed anyone's work in the audience. If so, you can let me know in the Q&A section. But there has been quite a bit of work in the 1.55 micron wavelength regime, as you can see here, using various deinterleaver architectures. Also shown in this list are their channel separation, crosstalk, insertion loss, and tuning power where reported. We've also listed our work in comparison here, indicating that 3.5 silicon deinterleavers can achieve low crosstalk with really low reconfiguration power consumption in the tens of nanowatts. Now, if these devices were perfectly fabricated, tuning power would be low for any material system that one uses, but we actually show in later slides that we can improve crosstalk from say 5 dB to greater than 30 dB with still only like tens of nanowatts of power consumption compared to the more power hungry thermal tuning counterparts. So our single mode hybrid structure is shown on the upper left-hand corner. The wafer bonded 3,5 region is a moderately doped 150 nanometer thick gallium arsenide layer. Here we have a cross-sectional SEM image of what the device looks like. And over here is a TEM image of the bonding interface in this. And so for this particular image, we used a combination of hafnium dioxide and aluminum oxide. So the figure on the bottom left here shows the simulated effective index change, which corresponds to the left axis, and the associated free carrier absorption loss indicated on the right axis versus voltage bias. And so this is done for several dielectric thicknesses of aluminum oxide, and then the same is done for hafnium dioxide on the right. So to put these values into a V pi L figure of merit, if we assume a length of 500 microns, an aluminum oxide thickness of 5 nanometers will have a static V pi L of 0.13 volts centimeter. For higher K dielectrics such as hafnium dioxide, a thickness of 5 nanometers will have a static V pi L of 0.09 volts centimeter. So on this slide, we compare experimental and simulated refractive index changes of our MOSCAP structure. So we actually fabricate our device on a platform with 3 different variations, and I'm going to indicate the variations, design 1 up to 3. And they have different varying amounts of silicon doping and also different gate type. Design 1 has aluminum oxide gate. Design 2 has a combination of hafnium dioxide and aluminum oxide. Design 3, very similar. It's thinner, but the silicon is not doped. And so the graph on the left here shows calculated index changes of various aluminum oxide thickness, again, versus bias. And we compare that to measured results indicated by the purple squares. So the measurement points point to either an effective index of 15 nanometers or a different refractive index of the dielectric, which can come from process variations. Likewise, for the hafnium dioxide, measurements indicated either a larger effective thickness or a change in the refractive index. But we're currently investigating these issues with TEM imaging and CV measurements. Okay, so this slide here shows the various types of MOSCAP deinterleaver architectures we've investigated, and they include second order and third order AMZIs, also 1, 2, 3 ring assisted AMZIs, and also second order cascaded ring filters. So each design has its own advantages and disadvantages in terms of passband flatness, passband roll-off, insertion loss. But we won't get into those things in this talk. So here we show results for the measured optical response for a second order MOSCAP AMZI deinterleaver before and after phase correction, the left being before and the right being after. So in this particular type of design, errors in the 3 coupling ratios and the path length difference can contribute to non-ideal passband response with reduced channel crosstalk. And as shown here, the cross and bar channel indicated by the orange and blue curves exhibit crosstalk of approximately 10.1 and 18.8 dB respectively. With appropriate modeling using transfer matrix calculations, it was determined that the biggest errors came from the first coupler being 35% instead of the required 50%, as well as finite error in the path length difference. But by applying a -1 volt bias on the first delay length, the crosstalk of the bar channel was improved from 10.1 to 15.3 dB and 19 dB up until 22 dB. Here we show results for a third order MOSCAP AMZI deinterleaver. Modeling shows that non-ideal passband transmission again comes from the first three couplers being 35, 18, and 18% instead of the ideal 50, 29, 29%. So even with the errors in the coupling coefficients, we are able to correct for the path length errors with the appropriate bias conditions indicated right here. So as a result, the crosstalk in the bar channel was improved from 7.9 dB to 28 or even 32 dB, while the cross-channel crosstalk improved from 4.6 to 22 dB. So it'd be ideal if we can tune the couplers with these MOSCAP structures, and we're actually looking into that as well. So here we show results for one ring assisted AMZI deinterleaver before and after phase error correction. Measured bar and cross channel exhibit about 7 or 11 dB respectively before phase error correction. By applying -2 volts just on this delay path of the deinterleaver, we can improve channel crosstalk from 7.3 to more than 16 dB, and then 11 dB to maybe 27 dB. And so at a bias of -2 volts, approximately only 5 nanoamps was drawn. So this results in a tuning power consumption of about 10 nanowatts, which is pretty low. Now, if you look at these pass bands, they're far from ideal from the theoretical flat top response if you were to calculate it. And this indicates a combination of waveguide loss and errors in power coupling coefficients. Usually non-flat top response is mainly attributed to waveguide loss, where you see this rounding, whereas increased channel crosstalk indicates more of a non-ideal power coupling in either your MMIs or directional coupler. Here we go one step further and show a two-ring assisted deinterleaver. In this case, we were able to improve crosstalk from 4.7 to 21.5 dB, and then 4.3 dB to close to 21 dB respectively. So in summary, we've demonstrated for the first time various 3.5 silicon hybrid MOSCAP deinterleavers with different architectures. The second and third order designs have crosstalk levels down to 22 to 32 dB with a tuning power of 83 to 53 nanowatts. The 1 and 2 ring assisted designs have crosstalk levels down to 27 and 22 dB with tuning powers of 10 and 7K nanowatts respectively. This value is a little high. We're not sure why, but maybe there could be that could be an issue from the fabrication. But overall, we think these devices are potentially useful for not only datacom or optical interconnects, but for large-scale neural networks and programmable photonics, which require low power. So yeah, that's a summary. And just in addition to the summary, just quickly, I wanted to mention that at Hewlett-Packard Labs, we have R&D interests in the EU, specifically photonics and the use of photonics in AI and quantum computing. So we're always looking for consortium partners and EU funding opportunities. And if you're interested, feel free to reach out to me or my colleague, Thomas van Verenberg. He's based in Belgium. Yep, thanks.